in continuation to the previous class, we have seen yesterday the parallel vectors and collinear vectors, and in that one, the important vectors are coplanar vectors. What does it mean by coplanar vectors? See, whenever three vectors lie on the same plane, then we call them as coplanar vectors. There's a little confusion between the vectors and the points. If you take any 3 points, A, B, C, which are non-collinear, in general, what happens? If you imagine a point A in the east, imagine another point B in the south, imagine another point C in the north, then obviously these 3 points form a plane. That means you need not have to find out, or you need not have to think about any 3 non-collinear points in the space. 3 non-collinear points in the space are always coplanar. Always coplanar. Then, how do we check the collinearity? What should we check for the coplanarity? What should we check for the coplanarity? That is, if there are 3 points A, B, C, which are non-collinear, obviously they form a plane. And if you take any 4th point D, then that 4th point D must also lie on the same plane. Then we call it as the coplanarity. If the 4th point D is not lying on the plane, then we say that these 4 points are non-coplanar. Let me show you that. For example, if I take just a moment, please. Yeah. 3 points that are marked. 3 points that are marked. If they are forming a plane, if the 4th point is also lying on the same plane, then I said that is said to be coplanarity. For example, if I take a point A on the east side, what I said, A is taken on the east side and B is taken on the south side. For example, just for imagination, you must have good imagination because you're all would be professionals and would be engineers of the country. You must have good imagination. And you have to draw many diagrams also, lively diagrams for constructions and all this. So consider another point C on the south side. Then, do you think that you have to discuss about the coplanarity of these 3 points? No need at all. No need at all. Obviously, wherever the points are lying, 3 points are lying, those 3 points definitely form a plane. So coplanarity is not to be discussed. Coplanarity is not to be discussed about 3 points. That the coplanarity is to be discussed about 4 points. If you take any other point D now, if this point D is lying on this plane of ABC, on this plane formed by ABC, then we call it as the coplanar. We call these 4 points as coplanar. If D is not lying on this plane, then we call it as non-coplanar. Then how do we proceed with? See, if these are the points we are talking about. If you want to talk about the vectors, then what we do now? Simply we will find out AB bar, AC bar, AD bar. Then if these 3 vectors are lying on the same plane, then we call these 4 points A, B, C, D are coplanars. So the vectors are formed by the points here A, B, A, C, and AD. So this is what you have to understand broadly, please. This is what you have to understand broadly. This is AD bar. This is AB bar. This is AC bar. This is AD bar. If these 3 vectors are lying on the same plane, then we call them as coplanar. This is about the coplanarity. That's okay. And we understand, I hope you understand what I'm explaining here about the coplanarity. Yes or no, please?
Yes, sir.
Yeah. Then what is that condition to be algebraically proved? What is a working rule to find out whether these vectors are coplanar or not? Let us see that. Let us see that. Now, what I'm doing, I'm taking up a vector which is lying along another vector, A bar, and taking up another vector, B bar. And of course, just now I said, you need not have to think about 2 vectors or 3 points. You need not have to think about 2 vectors or 3 points coplanarity. They are always coplanar. 3 points or 2 vectors are always coplanar. You need not have to think about that. Except the case of skew lines. Except the case of skew lines. Skew lines, you'll be getting that later. So let us take 2 vectors like this. Now, there is another vector which is coplanar to this. Then we want to understand what is the algebraic relation between them. So let me choose a vector here. This is, let me name it as the point C, whose position vector is C bar. I am naming this as O, and this is a vector C. Now, what I'll do, I'll be simply completing a parallelogram. I'll be completing a parallelogram with the help of C, point C. How to? See, I'm drawing a line which is parallel to B bar like this. Okay. Similarly, I'm drawing another line which is parallel to A bar like this. My task is to form a parallelogram. So a parallelogram is formed now. Now, very important thing, what I explained you yesterday. Let me name this. This is OA. This is OB. Now, OACP forms a parallelogram. Is it clear? Now, understand, OA is a part of A bar. Yesterday, I explained you a concept of coplanarity, collinearity, and parallel conditions in vectors. For example, if you take this line, I'm just revising that what we have learned in the previous class. This is a vector AB or a line segment AB. And if I take C as its midpoint and D as the midpoint of AC, then what is the relation between AC and AB? AC is half of AB. And what is AB? It is 3 times of AD. So when they are lying on the same line, or when they are collinear, or even for parallel also, what I said is there exists a linear relation between those segments there. Let me convert them as vectors now. AC bar, AB bar, AB bar, AD bar. There exists a linear relation between them. This is what you have to understand. So why should we write that? Why should we write that? If I write something like X into A bar here, you should not think like, why should we write this? What I'm saying, because OA is a part of A bar, I'm writing OA as XA bar, please. Where X is a non-zero scalar. Where X is a non-zero scalar. I think it is clear for you. OA is a part of A bar, and hence OA must be some X times of A bar. That's what I explained you clearly here. Whenever they are collinear, there will be linear relation between them. That's what I wrote here. Do you tell me OB in that case? Any one of you, please? What do we write? What do we write OB, please, in terms of B bar? In terms of B bar, please, because OB is a part of B bar. Respond, please. Respond.
Sir, OB in terms of B bar, sir, some Y into B bar.
Very good. Very good. That's it. Okay. Now Y into B bar. Then what will be CA bar? AC bar is also Y into B bar because it is parallel and equal. You can say that. Okay. This is BC bar is also X into A bar. Now I'm applying the triangle of addition. You tell me triangle of addition here. I can write OC bar as OA bar plus AC bar.
AC bar.
What is AC bar again? Because it is parallel to OB bar, it is also YB bar. Now your OC bar is nothing but C bar here. We have taken it to be C bar. And what is OA bar? XA bar plus YB bar. So if they are coplanar, there exists a linear relation between them. If they are coplanar, there exists a linear relation between them. So linear relation is this one. So if there exists a linear relation between the vectors A bar, B bar, C bar, then confirmedly we can say that. Confirmedly we can say that they are coplanar. This is what you have to understand, please. This is what I derived here. Now you can see what are the vectors here. OA bar is one vector, OB bar is another vector, OC bar is another vector. These three are lying on the same plane. Same plane. When they are lying on the same plane, obviously there exists a linear relation between them. If they are not lying on the same plane, we say that we do not get any linear combination like this. We do not get any linear combination like this. When we work out the problems, you will understand exactly how the linear relation does not exist, how the linear relation exists, and all this we will understand. So now let us generalize this. Let us generalize this. What I mean to say by generalization, we have derived a condition here. So what is that generalization here? A bar, B bar, C bar are coplanar. Coplanar implies there must be a linear relation between them. A bar is equal to XB bar plus YC bar. There exists a linear relation between these three vectors A bar, B bar, C bar, where X and Y are non-zero scalars. Where X and Y are non-zero scalars. So, what is that to be found out in case of coplanarity? If you are given three vectors, you must form a linear relation between them. If this linear relation exists, then we say that they are coplanar. Okay. Now, this is about the coplanarity. So, what is the final conclusion here? How do we decide and how do we understand the coplanarity? 3 points in the space which are non-collinear always forms a plane, always lie on the plane. If the fourth point D is also lying on the plane of ABC, then we say that the points A, B, C, D are coplanar. Coplanar. Now, if you want to see them in the form of vectors, then we form three vectors: AB bar, AC bar, AD bar. If AB bar, AC bar, AD bar are lying on the same plane, there exists a linear relation between them, like A bar is equal to XB bar plus YC bar, where X and Y are any two non-zero scalars like this. Okay, this is about the coplanarity. Okay, now let us continue. Let us continue with the theory. Yeah, now this is. Yesterday I discussed this. We finished that previous problem there. We have got the DCs of this vector. How to find the DCs? Dividing throughout with root over x square plus y square plus z square. Now properties of vectors, addition of vectors. Triangle of addition I have explained to you yesterday in the previous class itself. Parallelogram law of addition also I explained to you. We need not have to discuss that. And addition in component form. Component form means any vector can be expressed in three components: x component, y component, and z component. So if two, that is nothing but the 3D form. Understand that, please. 3D form. 3D form, 3 dimensions. It will be expressed in 3 dimensions, A1, A2, A3, B1, B2, B3. So how do I add them? Corresponding coefficients must be added. I bar coefficient A1 plus A2, J bar coefficient A2 plus B2, or K bar coefficient A3 plus B3. Like this, it is to be added. Okay. Now, properties of vector addition. What is the properties of vector addition? Binary operation. The sum of two vectors is always a vector, obviously, and the two vectors can be added only when they are in the same direction. Then only they can be added, or otherwise you have to apply the triangle of addition. Triangle of addition. Triangle of addition. And commutativity also, in the previous session I proved it using parallelogram law of addition. So
Yes,
A
sir.
bar plus B bar is equal to B bar plus A bar. That is always there. And associativity over addition. A bar plus of B bar plus C bar is equal to A bar plus B bar plus C bar. And identity means whatever the vector is there, if you add 0 bar to that vector, you'll get the same vector. You'll get the same vector, that is 0 bar plus A bar is equal to A bar plus 0 bar. So similarly, additive inverse, like in the real number system also, you know that. For example, if I take a real number 2, what is the additive identity of a real number system? Plus 0 is equal to 0 plus 2 is equal to 2.
2.
So
Yes, sir.
0 is the additive identity in the real number system. Similarly, 0 bar, because it is given in the bold letters. Bold letters means it is a vector. 0 bar is additive identity in the vector system. Similarly, additive inverse. Additive inverse means if you take 2 here in the real number system, what is the additive inverse of 2? Minus 2. That means if you add additive inverse to the given number, then you must get the additive identity. Then this is called additive inverse. So what is additive inverse of 2? Minus 2. Similarly, additive inverse of vector A bar is simply minus A bar. So all the rules like real number system only applied here. Next, subtraction of vectors. It is based on the triangle of addition only. Like you can see that subtraction of vectors, how it goes. This is, just what we have learned yesterday. I'm showing it again. This is OA bar, A bar, and OB bar, AB bar, B bar. Then what is the resultant vector? OB bar is nothing but A bar plus B bar. Now I want to understand the subtraction here. So when you take exactly opposite direction vector, the vector which is exactly opposite direction to B bar is nothing but minus B bar. You know that, I need not have to tell you. They are equal but opposite in direction. That is where minus comes out. Now, similarly, if you join this O to B dash here, what is B dash here? It is just the image of B, I can say, in the vector OA. The lengths are equal here. Lengths are not, we should not say it as image because it's not perpendicular. Okay, just we can take it as the length AB is there, B bar, and length AB dash is there, minus B bar. Okay, now if you join these two, again apply the triangle of addition for this. What happens now? This is A bar, this is minus B bar. So OB bar is A bar minus B bar. So OB bar here is A bar plus B bar, and OB dash bar, this is OB dash here. OB dash bar is nothing but A bar minus B bar. So there's no difference between addition and subtraction, except that B bar is to be extended backwards because we want to see this as a negative vector, minus B bar. So nothing more to discuss about the subtraction of vectors. Okay, now let us move on to property. That is done. Now properties of vector subtraction, very important thing is that even in the real number system also it applies. That is A bar minus B bar is not equal to B bar minus A bar, because if you take something like 2 minus 1, it is not equal to 1 minus 2. No, in the real number system also the same property. There is nothing special in this one. Similarly, the very important thing to be remembered in the higher level problems also, particularly in the objectives, the very important inequalities that are to be remembered are this. Modulus of A bar plus B bar less than or equal to mod A bar plus mod B bar. Modulus of A bar plus B bar is greater than or equal to mod A bar minus mod B bar. Modulus of A bar minus B bar is less than or equal to mod A bar plus mod B bar. Modulus of A bar minus B bar is greater than or equal to mod A bar minus mod B bar. So I'm not going to prove this, but I'll give you a hint how to remember that. I'm going to give you a hint how to remember that. By equality is possible when they are collinear, please remember. What is that to be understood broadly? Just let me show you that. Let me show you that. See, now there are two vectors here, A bar plus B bar. And you want to split them. Of course, these are in under the modulus. And you want to split them as mod A bar plus mod B bar according to the need. And you want to split it as mod A bar minus mod B bar for some purpose. Then you should not write is equal to always. Is equal to can be written only when they are collinear. Remember that. When they are collinear, then only you can write that. Then how to do this? How to do this? Very simple. Please listen to this carefully. Now what I'm saying, I'll take A bar. We will understand this. We will remove the vector. We will remove the vector. Let us understand this through real number system. Through real number system. What I'm doing, I'm just taking A bar as some 2. Because just to remember this, I'm giving you a hint here. Let us understand this as 2 and B bar as something like minus 1. I'm converting them to lengths now. Lengths. A bar length is 2. Let us suppose B bar length is minus 1. Then what is 2 minus 1, please? What is modulus of 2 minus 1? Respond, please. Respond.
Sir?
This is what is its value if you put A bar 2 and B bar minus 1? 1.
3, sir. 1, sir.
1. 2 minus 1, 1.
1,
Now,
Yes,
what
sir.
is mod A bar? 2. What is modulus of minus 1, please?
1, sir.
1, sir.
So what is 2 plus 1 here?
3.
3.
3,
What is 2 minus 1 here? 1.
1,
Which is greater? RHS is
3,
greater.
sir.
And hence
RHS
this is
side.
always less than or equal to. Just if you forget the inequality, what the hint I'm giving you, just follow this to write the correct inequality. So always A bar plus B bar is less than or equal to modulus of A bar plus modulus of B bar. If both are of the same sign, then that will become equal. And equality, geometrical, you have to understand like this. Geometrical, I'll tell you like this. See, for example, if you take a line like this, if you take a line like this is a line. Okay, now I'm marking the points on it. A, B, C. Now, if you write AB plus BC, obviously it is equal to AC. In this case, no problem. You can split it. Mod AC bar can be split as AB bar plus BC bar because they are lying on the same line. But in all other cases, it cannot be. So modulus of A bar plus B bar. Equality is possible when they are lying on the same line or collinear. And
Okay.
otherwise, it is less than or equal. Now, it is understood. If you want to split it as modulus of A bar minus modulus of B bar, then do you tell me, please, what should be written here? I'm writing this again. Modulus of A bar plus B bar. Take any two values here for A bar and B bar and tell me the inequality, whether it is less than or equal to or greater than or equal to. Yes, please, respond.
Sir,
Whether it is
Less than-
greater than or equal to or less than or equal.
greater than or equal.
Greater than or equal to, sir.
Correct. Greater than or equal. You can check with some two positive values there. 2, 1. 2 plus 1, 3. 2 minus 1, 1. Obviously, it is always greater. Similarly, if you want to write the same for modulus of A bar minus B bar also, you can check it out in the similar manner, modulus of A bar minus B bar. And if you want to see this as modulus of A bar plus modulus of B bar, then what is the inequality between them? Modulus of A bar minus B bar. So modulus of A bar minus B bar is greater than or less than? You tell me, please. You tell me.
The mod of A bar minus B bar less than, sir.
Correct. Similarly, modulus of A bar minus B bar, please, with respect to modulus of A bar minus B bar. I'll take it in this way. I'm taking this 2, like I have taken above, minus of minus 1. It is 3. Now it is 2 minus 1. Which is greater among these two? This one only greater. So these are the inequalities and these are reversed. Just check it out. These are reversed. Okay. Now these are the inequalities, and even in the two-dimensional geometry, we take them as triangular inequality. Triangular inequality. Okay. If it is any sum of any two sides must be greater than the third side. Triangular inequality. Okay. So here, just remember them like this. Now, just let us check it out now. Let us see this now. What is that given? What I mean to say, why I have given you that hint, you need not have to by heart, and you can simply use the real number system to write these inequalities. Modulus of A bar plus B bar less than or equal to mod A bar plus mod B bar, and modulus of A bar plus B bar greater than or equal to mod A bar minus mod B bar. Modulus of A bar minus B bar less than or equal to mod A bar plus mod B bar. Modulus of A bar minus B bar greater than or equal to mod A bar minus mod B bar. Now, coming to the next part of it, multiplication of a vector by a scalar. Obviously, what happens if you have a vector like this? A bar is there, a vector. Then if you multiply this vector with the 2, what happens? It becomes the length of the vector 2A bar is twice the length of the vector A bar. And we write it as A cap. A cap gives you the direction, and this gives you the length. So whenever a vector is multiplied with a scalar, its magnitude will be k times. If it is multiplied with k, that's what is given there. Just check it out. Multiplication of a vector by a scalar. If A bar is a vector, and M is a scalar, that is a real number, then MA bar is a vector whose magnitude is M times that of A and whose direction is the same as that of A bar. If M is positive and opposite is that of A bar, if M is negative. M positive, then that will be the same direction. If M is negative, that will be the opposite direction. So that's what it is about the multiplication of a vector by a scalar. Generally, what happens, why he is discussing all this, the algebra of vectors. The title of the topic is Vector Algebra. Algebra of vectors. So algebra means you must know the addition, subtraction, and multiplication of a vector by a scalar, and whether they are commutative, associated, all this. That is the reason why we have to understand all this geometrically. So multiplication of vector by a scalar is like this. Next, two vectors multiplied, you can understand that. We need not have to discuss more about that. Similarly, resultant of two forces R bar is equal to P bar plus Q bar. Mod R bar is equal to root over P square plus Q square plus 2PQ cos theta. This is parallelogram law of addition. Parallelogram law of addition. And this is, you can, and I think you might have applied this in physics by now. In physics, it will be used. Let us discuss more about this in the problems. Okay. Now, this is most important one. Is the next one is the internal angular bisectors. Internal angular bisector. What does it mean by internal angular bisector and external angular bisector? Just check it out. If you have a vector here, A bar, this is another vector, B bar. Now, the angle between them is bisected by, another vector, which is internal angular bisector. And there is another external angle is also there. This is external angle. There is another external angular bisector is there between them. Just a moment. This is external angle. This is internal angle. This is called internal angular bisector and this is called external angular bisector. Very simple is that how to get the internal angular bisector. By addition, you will get the internal angular bisector. By subtraction, you get the external angular bisector. Obviously, it is understood that this is A bar, this is B bar, and this is A bar minus B bar. A bar minus B bar. See, that is, if you take its reverse direction, opposite direction. I'll show you like this. This is one direction. This is another direction. This is another direction. Then you can say, this is A bar, this is B bar, and unit vector along this internal angular bisector is A cap plus B cap. So unit vector along the external angular bisector is A cap minus B cap. Understand this carefully, please. Understand this carefully. So what is the conclusion here? What is the conclusion? Just a moment. Let me make you remember this well through the diagram. I'll draw it. Just a moment. I'll draw it. Now, what I'm doing, just take a vector, which is A bar. Take a vector, which is A bar. Take another vector, which is B bar. Now, I need the internal angular bisector of these two. This is the internal angle. Now, what is the internal angular bisector? Obviously, it bisects the angle between these two vectors. Then it goes like this. It goes like this. Now, is it possible to write the position vector? Is it possible to represent this vector, which is in that blue color, which is known to be the internal angular bisector, which is known to be the internal angular bisector? This is A bar, please. This is B bar. This is, let me say, O. What I'm saying, if this is the internal angular bisector, let us understand about this. Now, if you write A cap, A cap, and what is a very, very important property with regards to internal angular bisector, even you learn in two-dimensional geometry also. Two-dimensional geometry also. Are you there, both of you?
Yes, sir.
Now, the perpendicular distance, listen to me carefully, please. The perpendicular distance from any point to either of the vectors is same. I'll change the color so that you'll better understand this. See what I'm saying? You take any point, you choose any point here.
On the angular bisector, sir.
For the angular bisector. On the angular bisector, choose any point. If you find out the perpendicular distance from B bar to this point, and similarly find out the perpendicular distance from the same point to A bar, these two are equal. Understand this? These two are equal, please. So whatever the point you choose now, that will be equidistant from the two vectors, two lines. Even in two-dimensional geometry also it is the same. So that is a property of internal angular bisector. Please understand that. Every point on the internal angular bisector or external angular bisector is equidistant from the two lines. Equidistant from the two lines. So now what happens now? In such case, there exists such a point on the line. There exists such a point on the line whose midpoint is lying on the angular bisector. I repeat. There exists such a point on the line whose midpoint will be lying on the line. Not exactly this one. I'll tell you because we have to take the perpendicular distance. Let me try in that way. Perpendicular distance. Now, if you take like this, maybe what I'm telling you, just there exists such a point which is whose midpoint will be lying on the internal angular bisector. So what we do now, we express a unit vector on A bar. This is A cap. We express another vector along B bar as B cap. Then we can simply say that A cap plus B cap divided by 2 definitely lies on the internal angular bisector. Definitely lies on the internal angular bisector. So what we do, it will be definitely some lambda times of A cap plus B cap gives you the internal angular bisector. According to the given condition, we will find out the lambda value. So internal angular bisector will be given by lambda into A cap plus B cap. Then now, do you imagine how the external angular bisector goes? External angular bisector goes. This is exactly opposite to A bar. This is B bar. Correct, no?
It's the external opposite direction of A bar angle, which external angle bisector is the bisector which bisects the angle between the opposite side of A bar and B bar.
Yes, that is the external angle bisector. So we can call it as minus A bar.
Yes, sir.
And this is the external angle. Then whatever the angular bisector is there for this angle will be represented like this. And obviously that will change the sign. If it is A cap plus B cap, this will be something like A cap minus B cap or B cap minus A cap. Makes no difference. Makes no difference. That sign will be taken either plus or minus. If you take this direction also, you can even write for this also. What I mean to say, I'll show you like this. I'll show you. See what I mean to say here. If I take the negative direction of B bar, what happens? It will go like this, no? It will go like this. This will be minus B bar. This will be minus B bar. Then what happens? This angle can also be taken. What I mean to say. These two angles are opposite angles. No, this angle can also be taken. Then what happens? You will get either B bar minus A bar or A bar minus B bar. Both are same. So we'll take it as plus or minus. That's what I mean to say here. We'll take plus or minus. So it can be done with both. So here, what happens now in this case now? Either this or this. It will be taken in the extended form like this. Similarly, it can also be taken in this direction. Are you there?
Yes, sir.
Yeah. Now, do you tell me how to write this yellow color external angular bisector in terms of A bar, B bar?
Sir, yellow color?
In terms of A bar, B bar, how to write this external angular bisector, yellow color vector. I'm talking about this one. Because it is written as lambda into A cap plus B cap, no?
Yes, sir.
Then this can be written as mu into something.
Yes.
You change the scalar. Mu
Yes.
into A cap minus B cap. Are you there? Do you understand
Yes,
what
sir.
I'm saying? Correct, no? So the conclusion here. Conclusion here. Angular bisectors of A bar and B bar. You have good number of previous questions on this one, please, and the objectives. Now we simply write it as lambda into A cap plus or minus B cap. That's it. Lambda into A cap plus or minus B cap.
Yes, sir.
Plus gives you internal, minus gives you external. That's it. Now, or otherwise, you can see this in the books if you refer, if you have the habit of reading. If you have the habit of reading, of course, you're all busy people, you never refer the books. But if you refer to the books in the synopsis or in the derivations, it can also be given like this: A bar by mod A bar plus B bar by mod B bar. Do you understand what I'm saying here? This lambda is a scalar, which gives you the length of the internal angular bisector. Which gives you the length of the internal angular bisector. So lambda is 1, that becomes a cap plus or minus b cap. So plus gives you internal angular bisector, minus gives you external angular bisector. And you should not forget this very, very important concept, which you will be getting questions on this one. Okay, now I've been telling you, I'll be showing this vectors in terms of 3D and 2D. If you want to understand this for 2D lines, let me tell you that. This is also important with regards to 2D line and explaining you this. Follow this carefully, please. We have two lines here. This is one line. Are there, Pranit?
Yes.
Pranit Babu?
Yes, sir.
This is another line. I'm talking about two-dimensional line, both of you. This is L1, let me say. This is L2. Okay, L1, let us name it A1x plus B1y plus C1 equal to 0. L2, let us name it A2x plus B2y plus C2 equal to 0. Now, let us see here in this case, you will have acute angle bisector in 2D. And this is obtuse angle bisector. Are you there?
Yes, sir.
Yeah. Acute angle bisector. Acute angle bisector is the bisector which is bisecting the acute angle between them.
Between L1 and L2, sir.
Yeah, this is acute angle bisector.
Okay, sir.
And the line which bisects the obtuse angle is nothing but the obtuse angle bisector.
Okay, sir.
I think it is very clear for you.
Clear,
Okay.
sir.
Now the same property we also apply here. What we applied in case of the vectors. In fact, it is extension from 2D to 3D only. The property you must be very clear. The property is that whatever the point you choose on the internal angular bisector or external angular bisector, that point is always equidistant. That point is always equidistant from the first line L1 and from the second line L2. That means these two distances are equal. These two distances are equal. In other words, we can say that they are equidistant. They are equidistant means this distance is same as this distance. So the locus of the point which is equidistant from the two lines is nothing but the angular bisector. The alternate definition, in fact, it should be the definition. The locus of the point that are equidistant from any two lines is nothing but the angular bisector. Now, if you want to see the formula related to this, which is very much similar, if you understand like this, entire vectors and 3D or 2D comes under the same umbrella. What I mean to say, this is the locus we have to find out. Let me say this as P. P, let us take it as XY. Do you tell me the perpendicular distance from a point P to the line? Any one of you? I repeat the question. This is a point P, XY.
Yes,
Let us suppose X1, Y1 or X0, Y0. What is its perpendicular distance from the line L1, please? Perpendicular distance formula.
So on perpendicular distance from a point to line, sir.
Yes.
Point line.
Let me say this as PA.
Sir, 1 minute. Sir, A1, AX1 plus BY1
That's it.
plus C.
That's it. PA, PB. Now, Pranit, PA is equal to PB. Why should it be? Because it is angular bisector. It is a point on the angular bisector.
Yes, sir.
Come on, tell me PA, please. Perpendicular distance from this point to this point. Modulus of A1x
Plus B1y
plus B1y.
plus C1
Correct. Divided by
under root
√A1
A1
square.
yeah A1 square plus B1 square.
That's it. Is equal to PB, please. PB. This is the line. Second line, L2. Come on, tell me. Modulus of
A2x modulus of A2x plus B2y plus C2 by under root
yes.
A2 square plus B2 square.
Very good. Correct, no? Now remove the modulus. Remove the modulus, then you will get the formula for angular bisectors like this. A1x plus B1y plus C1 divided by √A1 square plus B1 square is equal to plus or minus A2x plus B2y plus C2 divided by √A2 square plus B2 square. I hope you understand what I'm saying there.
Yes, sir. Understood, sir. Clear.
So plus gives you one angular bisector and minus
Okay,
gives
yes,
you
sir. Yes, sir.
another angular bisector. Then you must be asking me, sir, how do we extend this to three-dimensional geometry? Because you never ask, I have to pose a question on my own and I have to answer it, no? So that is why I am posing the question to myself and I'm answering it. But let me expect the answer from you. Like what? Plus gives you one internal angular bisector, maybe one angular bisector, and minus gives you another angular bisector. Then here also there must be, you must have a doubt here. So whether plus gives you internal acute angle bisector or obtuse angle bisector, and minus gives what? Plus gives internal or external, minus gives internal or external. That is again a concept to be remembered. That is, we will have another conditions for that one in two-dimensional geometry. Let us keep it aside. We will be discussing that later. But now, here my effort is to make you understand this in terms of three-dimensional geometry. What is that? In the beginning, I said the concept of every 2D line. Every concept of 2D line can be extended to 3D. In which form? Should I repeat the question?
Yes,
every formula or every concept of 2D line can be transformed to which form of 3D? Which geometrical figure of 3D? It's a
plane.
It's a plane.
Sir, said it now, sir.
Plane. Line is ax plus by plus c equal to 0.
Sir, I said it now. Plane.
Yeah, that's good. Line is ax plus by plus c equal to 0. And plane is ax plus by plus cz plus d equal to 0. So this can be comfortably extended to 3D plane. So let me show you that now. Let me show you. Now it's clear, but I did not explain you when plus is to be taken and when minus is to be taken for a particular acute angle bisector or obtuse angle bisector. You just verify, you'll understand. Anyway, we will be talking about that in the later classes. Okay, now how this will be extended to the plane, because we are discussing vectors and 3D. We are discussing vectors and 3D. Let me show you that. Let me show you that. I have taken a plane. Yeah. This is a plane, please. This is, I'm taking another plane. Yes. Are you there, both of you?
Yes, sir.
Now I need the internal angular bisector of this plane. And I'm naming these planes.
Yes,
I'm
sir.
naming these planes as, just like I named the lines, I'm naming these planes. P1, A1x plus B1y plus C1z plus D1 equal to 0. P2, A2x plus B2y plus C2z plus D2 equal to 0. Now, this is the angle. You have to imagine in 3 dimensions here. This is the angle, what I'm saying. This angle between the planes is to be bisected by another plane.
Yes, sir. Another plane.
This is the angle. I'm not a good artist, but I'll make you understand this. I'm trying to draw this. This is the angle between them. Now,
The A1x plus B1y plus C1zy plus D1 by A1 square plus B1 square plus E1 square is equals to A2x plus B2y plus C2z plus D2 by A2 square plus B2 square plus C2 square.
perfectly, but you must include
Internal.
perfectly.
Internal.
But you must include plus or minus there. That's it.
Yes, sir. Yes, sir. You asked for internally, so sir. If you add just the
that's
angular bisector, I would include both of them, sir, plus or minus.
No. One thing you have to understand that plus and minus again depends on conditions.
Yes, sir.
Depends on conditions. Like we will be discussing that. But for now, I'm making you to understand how the angular bisector will be. This will be now bisecting the angle between these two. Yeah, just a moment. This is the plane which is bisecting the angle between them. Then how do we understand this? Let me show you that. Let me show you that. Pranit? Pranit, Babu, are you there?
Yeah, sir, there, sir.
Yeah, that is a angular bisector. What I'd like to tell you here, this angle is now, this angle made by this plane with this plane is same as this side. These two are equal. Continuation, of course. Okay, now what Kaushik was saying is correct now. Now what I would like to tell you here, the extension of 2D geometry or extension of 2D line to 3D plane. So internal angular bisector or external angular bisector of these two planes is simply given by A1x plus B1y plus C1z plus D1 divided by root over A1 square plus B1 square plus C1 square. Pranit,
Yes, sir.
you tell me is equal to what? Plus or minus?
A2x plus B2y plus C2z plus D2 by under root A2 square
Perfect.
plus B2 square.
Plus C2 square.
Yes, sir.
That means you will get two planes here. One divides the internal angular bisector and other divides the external angular bisector. If you understand the concepts like this, it will be very easy for you to work out the vector algebra and as well 2D and 3D geometry. Okay, so whatever the concepts are there for 2D line, that can be straight away extended to 3D planes. That's what I mean to say. These are the internal angular bisector. Now this is shown in the vector form. What is the vector form we have taken? A bar plus or minus B bar into lambda I set. Do you remember? This is nothing but that plus or minus. Kaushik.
Yes, sir.
What happens now in three-dimensional geometry, the components will be splitting like this. In vector algebra, they are packed like this. That's only the difference. So you can even write it as lambda into A bar by mod A bar plus B bar by mod B bar. How do you see this now? Mod A bar, mod B bar are a very simple is that this mod A bar relates to this one. Mod B bar relates to this only. That's what you have to understand.
Yes, sir.
So if you see three-dimensional geometry and vectors like this, the concept will be very easy for you. Okay? This is about the internal and external angular bisectors of a 2D line and 3D plane. And as well, I have explained you how it is shown in the vector form and how it is shown in the 3D form.
3D form, yes, sir.
Now, let us see the related problems here. That's about the internal and external angular bisectors. And is the formula given there? I don't think here the formula is given. Okay, he has given it in this form. Just see. He gave it as mu into, just see this. This one, he gave like this. One is plus, other one is minus.
Minus.
Okay. Now, ABCD is a regular hexagon, then AD bar plus EB bar plus FC bar. Given in terms of AB bar, in terms of AB bar. So, let us write the question one moment. Let me write the question. ABCD, EF. Is a regular hexagon. Then AD bar plus EB bar plus FC bar is equal to, this is what we have to find out. The options you can see, they are given in terms of AB bar. So this entire thing is to be converted to AB bar only. Don't forget, according to the options are containing AB bar. You have to convert them only to AB bar. Can you try this, please?
Yes, sir, I'll try.
I'll draw the diagram. I'll help you out with the diagram. Let us take AB, CD, EF is a regular hexagon. Is a regular hexagon. Like this. Yeah. Kaushik and Pranit, are you trying it?
Yes, sir, trying it.
A, B, C, D, E, F. Now this is to be expressed in terms of AB bar. Now what are the properties that are to be taken
Sir,
here?
in terms of AB bar, sir?
Yes, yes, in terms of AB.
Okay, sir.
Now the property here is FC bar is double of AB bar. Because it's a regular hexagon. FC bar is double of AB bar. Okay. Now AD is double of BC bar. Obviously, AD bar is double of BC bar. These are the geometrical properties, and it is clearly understood. Now you try it, please. AD bar can be written as
say 2 BC bar, sir.
2 BC bar.
Yes, sir. EB bar can be written as 2 FA bar, sir. And FC bar can be written as 2 AB bar, sir.
AB bar, sir.
Come on, finally convert it to AB.
Yes, sir. AD bar plus EB bar is equals to 2 into BC bar plus FA bar. That equals to origin. This is the origin, sir. Intersection point of all.
Okay. I don't think we need that intersection there. AD plus you tell me now, instead of AD I can write twice BC now.
Yes, sir. Twice BC.
This is twice BC plus EB, please, EB.
Twice CD, sir.
Twice DC. You should
DC.
not change the direction.
Yeah. DC.
Come on, you work out.
So, 1 minute, sir. I'll tell you answer.
EB is, tell me that, Pranit, twice, EB is twice DC.
DC.
Next, FC is there, FC.
ED plus FC.
No, FC is double of?
ED, sir.
ED or AB? Both are same.
Yes, sir. Yes, sir.
Now we need this in terms of AB. In terms of AB.
AB can, okay.
The answer should be in terms of AB. DC is parallel to FA. And
Yes, sir.
BC is parallel to FE.
FE.
Sir,
Yeah,
4 AB bar, sir.
4 AB bar. Okay.
Yes, sir.
Now you continue this, what I wrote.
Sir,
You continue this. Can you do this? Twice BC plus twice
Yes,
DC. Instead of BC, or what is DC there? DC is parallel to AF, no?
no, sir. I did it another way, sir.
Yeah. Come on, tell me that.
Another way, sir. Sir, AD bar plus we wrote until this sir, FC bar equals to AB bar. We converted, sir, in terms.
Yeah.
So from AD bar plus EB bar is equals to twice of BC bar plus FA bar, sir. Yes, sir.
Okay.
So I took this point as origin, sir. O. Intersection point.
Okay. You took that. Okay.
Yes, sir. I wrote BC bar as AO bar, sir. Then I took in the triangle AOF. FA bar plus AO bar plus FO bar is equals to 0. FA bar plus AO bar equals to minus FO bar, sir. So AD bar plus EB bar equals to minus 2 times of FO bar.
Okay.
Then AB bar is equals to minus FO bar, sir.
Okay.
So AD bar plus EB bar is equals to twice of AB bar, sir.
Okay.
So we got AD bar plus EB bar plus FC bar. Now 2 AB bar plus 2 AB bar, sir.
Okay.
4 AB bar.
4 AB bar. Okay. Now, can we do with this one, because by keeping the twice AB as it is, can we work out the same
C bar
without checking that O? Is it possible?
1 minute, sir. I'll try it, sir. In terms of that.
BC is there. Let us keep it as it is, because we need AB. Let me keep like this. Twice DC can be written as twice FA.
Yes, sir.
Plus twice of AB.
Yes, sir.
Then twice FA, twice BC, FA, BC, FA, BC. Let us convert it to, what is there any common point here? FB, FB is FC. BC plus FA.
Yes, sir. For that reason only, I took the common point as O, sir.
Okay, okay. But without that also we can do, I think.
Yes, sir.
Twice BC can be written as FA.
Twice it.
Let us try like this. FA. FA can be written as FA can be written as FB plus BA. FA can be written as FB plus BA. Plus twice of AB. Now this is twice of BA, twice of AB gets cancelled. What is that remaining? Twice BC plus twice FB remaining. It is done. Let us see that it is done. Now what I'm saying here, this is twice BA, this is twice AB getting cancelled. Now if you take twice of FB plus BC, are you there?
Sir.
Why I'm taking this now? You can clearly observe this is E is common point. That is, it is terminal point, it is initial point. Triangle of addition.
Yes, sir. Triangle.
Triangle of addition. Then what happens to this? Twice of B will be removed and you'll get FC. What is FC? Your answer is same as my answer. Both are correct only. You did good. That's good. FC is nothing but twice of AB. Done. Your answer is 4AB.
Yes, sir.
Got the same, no?
Yes, sir.
That's it. So without me considering the point of intersection there, I did it in this way.
Yes, sir.
Okay?
Yes, sir.
Pranit,
Sir,
you have to proceed like this, and it is little confusing, and you
Yes,
have
sir.
to take the triangle of addition into consideration, and you must know these properties.
okay, sir.
Okay, it's obvious. Similarly, if you take EB, no, EB is double of what? EB is double of DC.
DC.
EB is double of FA also.
Yes, sir.
This is about the hexagon. Okay, is it done?
Done, sir. Clear also.
Next, the unit vector parallel to the resultant vector. Unit vector parallel to the resultant vector.
Resultant vector.
Kaushik, remove that line.
Yes, sir.
What are the vectors given? A bar 2, 4 minus
Y.
5.
B bar 1, 2, 3.
Correct. What is that we need?
Resultant vector, sir.
Resultant unit vector. Huh?
Yes, sir. Resultant unit.
Resultant unit vector. Let us see that. Resultant unit vector is equal to plus or minus A bar plus B bar whole divided by
Under root A bar plus B.
modulus of.
Model. Sorry, model.
Correct now?
Done, sir. Yeah. My mistake.
You can do that now.
Yes,
Come
sir.
on, tell me the addition there. Add this 2 plus 3.
3 plus
Right.
6 minus 2.
Correct. Divided by under root 3 square plus 6 square plus
Plus 2 square.
how much is it? Remember it as a triplet of perfect square. triplet of perfect square because 3 square, 9, 6 square, 36, 2 square,
49, sir.
added 49, that is
7, sir. 7.
7. So plus or minus 1 by 7 into
3i
3i
plus
plus 6j
6j
minus 2k. So this is a unit vector which is resultant of A bar and B bar. Clear, no?
Clear, sir.
Yeah. Next example 6 will be continued in the next session.
Okay, sir.